In this video we will see exactly what we see in the previous one, but we will move from r squared to r cubed and see what happens when we sum two vectors in r cubed and take their geometric associated points. We switch quickly from r2 to r3, adding an extra coefficient here in the two summands. Therefore, the same thing will happen here in the vector sum. Okay, so they are being replaced. The two summands are being replaced by the same first two coefficients and a new one, which we will call C as the third coefficient for the yellow dot, and F for the cyan dot. The vector sum of the two will have a third coefficient, which will be the sum of the third coefficients in the yellow dot, in the yellow vector and the cyan vector. As we have seen in the 3D representation of R3, we cannot represent these R3 vectors in a Cartesian plane, but we need to add an extra axis that it already appeared down here, and then switch and turn the view in order to have a three-dimensional view of the new coordinate system. We make the xy transparent because not necessarily the third coefficients will be greater than 0, therefore we allow them to be negative, and in that case we need to see below the xy plane. Okay, so we have the 3D situation in which in the xy plane we have the previous 2D picture embedded. We have to change the representation of the 2D vectors that we had before to the 3D one. So we have to add a third coordinate to the yellow dot and the cyan dot. So we are assuming in this case that both C and F are positive. Consequently, we have to raise the sum dot, the sum point, up to C plus F in the positive direction. Therefore, if this is C, this is F, exactly as we found the place in the coordinate axis in the 2D case, we do in the 3D case. Therefore, the Z component of the sum vector, which is C plus F, will be determined by the F of the cyan dot and the C of the yellow dot. So this is going to be C plus F at this height. Now we want to do the same as we have done in the two-dimensional case. Therefore, we'll be moving the two summands, yellow and cyan, and see how the sum, the point associated to the sum, changes. Okay, it would have been too complicated to leave all the projections in the coordinate axis and planes. Therefore, we just remove them to make the picture more less hectic. Okay, so as you see here, we have movement of the summands, the consequent movement of the points associated to the sum. And again, as the previous case, each coordinate of the red point is precisely the sum of the corresponding coordinate in the yellow and the cyan point. Now, how can we recover geometrical construction in the 3D case? Let's see if we can stick with the same or similar, at least, constructions as in the 2D case in this situation, in this three-dimensional situation. Let's see. Okay, so we can connect again the two summons to the origin with an arrow, and we notice that translating errors exactly like in the 2D case, we will end up getting two arrows with common ending point, which is precisely the sum of the two vectors. Okay, it will lie in some other plane, always passing through the origin though, not necessarily some coordinate one, as I just said. So the situation is very similar to the 2D case. Let's see now what happens to this construction when we change the two summons. Okay, so we see that the parallelogram changes shape, but it changes shapes and the plane on which it is embedded, but still is a perfectly defined parallelogram whose vertices are exactly the summons and the sum and the origin, and sides are these segments or this arrow that we have used to geometrically construct the sum of the two vectors. So exactly like in the 2D case, except that we have this twisting of the plane in which the whole situation is embedded.